Today, what I would like to talk about is, in fact, heterogeneous type of bilayers. So basically, the question that we pose ourselves is what kind of phases emerge when we bring together, when we bring in proximity a Mott insulator with a metal or a semiconductor. And in fact, there are various examples already of this type of bilayers, heterogeneous bilayers. One case, for instance, is the alpha ruthenium trichloride, which is a candidate for a Kitaev type of antiferromagnet. So where we have bond-dependent exchange interactions. And the question is what happens when we bring this system in proximity to graphene. But today I won't talk about this type of bilayers, but I will talk about this other type, which is also has similar type of features because we bring together 1T tantalum disulfide, which is a triangular lattice spin 1/2 antiferromagnet, which then it's a Mott insulator in proximity to a metallic system, which is the 1H tantalum disulfide. And basically what we want to understand is what kind of phases appear when we bring these two systems together, taking into account that we are going to have effects of strain, charge transfer, and hybridization. And this is a work we have done together with my collaborators that I will present in a moment, but where I want to show that the combination of density functional theory calculations with dynamical mean field theory is able to give us an understanding of what is going on in this system. So this is a system I'm going to talk about. And first of all, of course, I would like to acknowledge my collaborators. Without them, the work wouldn't have been what it has, what I'm going to show. So first of all, my PhD student, Paul Wunderlich, who finished in Frankfurt and now went to the industry. Lorenzo Kripa, who was a postdoc with Georgia and now is a postdoc with Tim. And then Bin Hai and his postdoc Hyung Hu from the Weizmann Institute. In fact, now Bin Hai moved to the US, so he is at the University of Pennsylvania, and also Igor Mazin. And of course, my colleagues Tim Welling and Giorgio San Giovanni. So let me start by introducing this bilayer system. So this is a 1T, 1H bilayer. So basically it's formed by two types of polymorphs of tantalum disulfide. So tantalum disulfide, and it's the same for tantalum diselenide, appears in two types of polymorphs. One case is the so-called 2H, where tantalum is in a trigonal environment of sulfur. And this type of system, in fact, is a metallic system. So it builds basically 2D triangular lattices of tantalum. And because the band structure, so basically the hopping between tantalums is much larger than the Coulomb repulsion, so we have a metallic. On the other hand, when tantalum appears in a polymorph where the surrounding sulfur built an octahedral environment, what happens with this type of layered system is that at about 300 Kelvin, the system undergoes a structural distortion in this fashion. So it forms what it's called the Star of David. So basically 13 tantalums, they come together and form this star where we have a tantalum at the center of the star and 12 building this star. And what is interesting about this type of charge density wave state is that the charge in this, in fact, the charge in this Star of David builds a molecular orbital where we have the center of this molecular orbital at the tantalum. It's a D2Z type of Wannier function orbital, which is as shown here by these calculations by Darren Sid and collaborators. And what it forms at the end of the day is basically a triangular lattice of this Star of David with one electron per side. So this is in fact antiferromagnetic triangular lattice where we have a very strong Coulomb repulsion between the Star of David and we have a Mott insulator. So now the question is, what happens when we bring this system together? And this is now what I'm going to show is first experimental results. So these type of bilayers have been now, in fact, grown with molecular epitaxial growth by various groups. And here I'm showing the typical results that are being observed. See, these are now STM measurements by building this type of bilayers. So what I'm showing here is the results by the group of Alto, by Lilienroth and collaborators. And basically what I'm showing here is the DIDV as a function of the bias voltage by putting the tip at 3 different places. So when the tip is put on top of the only 1T tantalum disulfide layer, so basically this charge density wave distorted system, what they observe is indeed a Mott insulator. So there is a big gap between the upper and the lower Hubbard band. When the tip is put on top of a 1H layer, then indeed they see a metallic behavior because we have indeed this triangular case of the 1H tantalum disulfide. However, when the tip is put on top of the bilayer, so here the red dot, it's a bilayer of 1T, 1H, what they observe is the appearance of this zero bias peak. And here what I'm showing on the right is the temperature dependence of this zero bias peak at high temperatures. It's very broad, but then it goes on appearing clearly by going to low temperatures. And moreover, this has been seen also in the bulk layered structure. So there is also the case of a bulk system created by 1T, 1H, 1T, 1H, which is the so-called 4HB tantalum disulfide. So there are experiments by the group of Heim-Beidenkopf where they indeed put the tip on top of the 1H or the 1T, and they observe similar behavior. So the question is, which is the origin of this zero bias peak? And the most natural answer to that would be, well, we may be having here Kondo physics. So indeed, because we have a Mott insulator, which very well localize spin 1/2 at the center of this Star of David. And then we have that this is hybridizing or interacting with the conduction electrons from the 1H tantalum disulfide. And what I want to show you now is that the answer to this question is not as straightforward. So there are a lot of subtleties that I would like to now talk about in the next minutes. So first of all, of course, let's have a look at what we are bringing here together and which are the ingredients that we have to pay attention to. So what we have is that due to the fact that we are bringing together 2 different types of systems, we are going to expect a different chemical potential. So they both have different work functions. And as represented here, so when we bring them together, depending on the distance that we have between the 2 layers, there will be a charge transfer because they have different chemical potentials. And what we know, in fact, and I will show that in a moment by doing first density functional theory calculations, is that at a critical distance, we are going to expect that all electrons from the 1T are going to be given to the 1H. So there will be a complete charge transfer of the electrons corresponding to this layer. And this is what I'm showing here. that if we consider the optimal distance, so these are now what I'm showing is calculations done by Hyung-Woo. These are density functional theory calculations done with GGA, PBE, and by including van der Waals corrections. So basically, by considering the relaxed structure of putting these two layers together, the optimal distance is 5.8 Armstrongs, which in fact corresponds to the distance in the bulk system. And what happens, we can see it here by looking, for instance, here, this is the band structure and the density of states, where we have colored here blue as the density of states coming from the 1T layer, and in gray, the density of states coming from the 1H layer. And as you can observe, there is a completely empty flat band, which is in the conduction band, because at this distance, we have a complete charge transfer of these electrons to the 1H system. And in gray, what we observe is the band structure of the 1H system. Now, if we, now if we go on bringing apart these two layers, so this is now a relaxed structure, but by keeping the distance between the layers at 6.3 Armstrong, then of course what is happening is that there will only be a partial charge transfer from the 1T to the 1H layer, and this can be observed in the electronic structure, where what we have now, I mean, these are now spin polarized calculations. What we have now is a partial occupation of this flat band corresponding to the 1T layer. And now what one can do is just the study as a function of distance between these two layers of how the electronic structure changes as a function of the distance. And there will be two effects that will play a role in whether we have charges being transferred to the 1H or not, which are on the one hand, this difference of chemical potential, but on the other hand, the fact that at a certain distance, especially at small distances, we have an important hybridization between these two layers. So this is all what we can learn from the DFT, that as a function of interlayer distance, we're going to have partial occupation of this 1T, and only when we bring the two layers very far away, we still keep the 1T layer where we have one electron per side, and then the conduction layer. But at these very large distances, there is no left hybridization between the two layers. So how do we bring that together with the interpretation of this zero bias peak that I was showing to you, and whether it's a Kondo type of behavior or not? And for that, we really need to go beyond DFT. And here is where the MFT is extremely helpful, because as you all know, the MFT gives us information about the local dynamical fluctuations in the system. And in fact, we will be able, with dynamical mean field theory, to disentangle what kind of screening effects do we expect in the system at different type of fillings, depending on which is the distance between the two layers. So on the one hand, of course, we will have effects of interlayer 1T, 1H hybridization, but because we are starting to have only partially occupation of the 1T, we can also expect screening effects coming from the hopping, basically the charge fluctuations within the 1T layer. So let me show you what we did with dynamical mean field theory. So first of all, because this is a huge system, basically the first step is to obtain a tight binding model from the DFT calculations for the different cases considered. So basically the tight binding model consists on including the Hamiltonian for the T layer. So the kinetic energy, here it's the on-site energy and the kinetic energy up to third neighbors. The kinetic energy for the H layer, for the 1H layer. And then, of course, we are going to expect a hybridization term between the H electrons and the T electrons, which I'm calling for nomenclature. The H electrons are the conduction electrons, and the T electrons are my D electrons. And what we are having here is basically 13 d orbitals per 1d orbit, so of the H layer per 1d orbital of the T layer, because we have in the T layer, if you remember, this Star of David, well localized the electron. And for instance, for a distance of 6.5 Armstrong, what we have is a charge transfer of about 0.5 electrons, and these are the corresponding the parameters that we have in our time binding. And now, as we had Song Sook already to give a nice summary of the DMFT, this is what we are doing. Here we are applying DMFT to this Hamiltonian, where the correlated orbital is this d orbital in the T layer. And what we are using is B2 dynamics. So the question that we want to answer here is, in fact, screening effects. What is causing a screening effects, and where does that come from? So a quantity which one can calculate in dynamical mean field theory is, for instance, the local static spin susceptibility for these correlated 1T electrons. And here what I'm plotting is this quantity as a function of temperature for first the case, the hypothetical case, that would be the, let's say, the typical Kondo case where I have in the 1T layer, basically that there is no charge transfer, so that we have one electron per site, localized, one magnetic moment, interacting with the conduction electrons of the 1H layer. And what I'm showing here is, as a function of the hybridization between these two layers, how is this local spin susceptibility behaving as a function of temperature? And we know that, in fact, this behavior gives us information of the screening. So if what we have that the behavior of this susceptibility follows a Curie type law, then this indicates that we have very poor screening. However, if we have considerable screening, we are going to expect a Pauli-like behavior. So what I'm showing here now is, for this case, at different hybridizations, the straight lines correspond to the fitting to this expression, to this Curie expression, and the dots to the calculations, the DMFT calculations. And as you can observe, only when we go to very large hybridizations, there is basically a deviation from the Curie behavior, which means that we can only have screening effects at very, very large hybridization. On the other hand, if you remember, large hybridization, it means necessarily that the two layers have to be very nearby, so we will have charge transfer. So this is a very hypothetical type of possibility. And moreover, another way of seeing these screening effects is by looking at this local spin susceptibility as a function of time. I mean, this is imaginary time, and the way it decays. So if we have strong screening, it decays very fast. If there is no screening, it decays very slowly, or almost no decay. And the values of hybridization for our system is the 60 milli-electron volts. So as we can see, there is almost no screening. On the other hand, now, if we introduce the realistic values so that we have charge transfer and we have a hybridization between these 1H and 1T electrons of about 60 milli-electron volts, and we look again at this local static spin susceptibility, what we observe is that at these realistic values, we do indeed have a deviation of the Curie bias behavior shown by the dotted line. So this is now in the blue case. And what we can extract is a screening scale when the screening effects start to be important. And now, of course, what we observe is that these screening effects here are coming from, have two sources. One is, of course, the hybridization with the conduction electrons in this 1H layer. But on the other hand, we also have screening effects here due to the fact that we have charge fluctuations because we are away from half filling. Now, how does these now show up in spectral functions? So again, sorry, maybe here again to show that these charge fluctuations in the 1T layer are clearly the dominant source of screening for this case. So how does that now translate in terms of the local spectral function? So if we now here plot the local spectral function for this quarter field case, so when there is a charge transfer of 0.5, so at the realistic values, then one can observe that the spectral function, basically as a function going down in temperature, it builds out this quasi-particle peak. Of course, it's asymmetric. And then here are the upper and the lower Hubbard band. While if we look at the case of no charge transfer, there is almost no appearance of this zero bias resonance. So now, basically, what comparing with experiments, we can compare the qualitative behavior of these results with the experimental observations. And indeed, this is what the experiments are observing, that as a function of temperature, there is the appearance of this asymmetric quasi-particle peak. And our interpretation of what it's being observed in experiments is that it's not due to a Kondo type of quasi-particle peak or zero bias peak that is appearing, but it is because we are having a heavily doped Mott insulator. So basically, we are a quarter field type of Hubbard system on a triangular lattice. Now, of course, and here are, in fact, many other measurements where one observes that even more clearly by finding these two asymmetric upper and lower Hubbard band and the appearance of this quasi-particle peak at the near the zero, so at the zero bias. Now, the question, of course, is here now I've been talking all the time about trying to understand the appearance of this zero bias peak in STM experiments. However, the question could come, are there other experimental probes where we could distinguish these two scenarios, heavy fermion versus the Mott? And in fact, this is because we had a question of one referee, which made us think about that. If you look now here at these two cases, so here I'm putting the heavy fermion type of scenario so that I have a half field case, so no charge transfer. The 1T layer is really one electron per site, and a strong hybridization with my conduction electrons. And here what I'm showing is the case of the with charge transfer, so the quarter field with so let me go back, with a smaller hybridization, but of course, the fact that I will be having a screening effects due to the fact that I have the 1T only quarter field. Now, if we look at the fitting of the local spin susceptibility as a function of temperature to a Curie type of behavior, so in this case, we are getting an effective moment of 1.45 and a Kondo temperature of 4.3 Kelvin. While in this case, I'm getting similar values. So how to distinguish those is indeed, for instance, by looking at the momentum-dependent spectral function. And here again, so here clearly one can see the different features of having a heavy fermion scenario versus having a doped mode. And for instance, in the heavy fermion scenario, so what we observe here is I'm plotting the band structure, so the DMFT band structure, where there is, of course, a very strong hybridization, which is not there in the quarter field case. And more important is, here is basically this picture here at high temperature and at low temperature, so these results, but this entangle in terms of the 1T and the 1H, that clearly in the heavy fermion scenario, as a function of temperature, what we see is a clearly reconstruction of the Fermi segments of the Fermi surface, which is not observed in this quarter field Mott dope Mott insulators, so in this correlated method. So this would be...
Can I ask a question?
Please.
I was a little confused because you mentioned screening, and then
yes.
what you showed was the spin local susceptibility, right?
Yes. Yes.
So do you mean, do you use the term screening in terms of reduction of the local moment?
Yes.
And, combo screening? Or do you really mean the charge sector, in which case one would have to look at the charge susceptibility, right?
Yeah, I'm meeting from the moment it's only for the spin sector. So all the screening I'm talking about is how much in the spin sector, the fact that I have just a partially filled D system, so 1T system, how much this is also influencing the spin susceptibility.
So it's really the reduction of the susceptibility as compared to Curie, right?
Yes, yes, exactly. So it's only looking at the spin sector, not at the charge sector. But already what one finds out is that at the level of only, for the fact that we are having not a localized moment at each side, but only on average have a localized moment, this also is giving screening effects in the spin sector.
Thank you.
I'm sorry, but just to follow, to make sure that I understand. Hi, Roser, by the way. This is all very interesting. But is the total charge in the two-layer system the same in both cases? And it's just a question of how the charge is transferred between layers? Or is it that one is really doped with respect to the other?
Exactly. So thank you. So indeed, that's the difference. In this case, basically, well, the charge here in this case, what I have is that the charge in the 1T is basically 1 electron per site. And I think that the question is whether I keep that the charge of the 1T plus the 1H, whether this total charge is kept constant,
exactly.
Right? Yes, yes, this is kept constant. So what we have always is that the system, the full charge is kept constant. It's only that there is a different charge transfer. So here there is charge transfer, but here it's not.
Yeah, understood. Great. Thank you very much.
Thank you. So so this was and now in fact the experimentalists are doing RPS measurements on this type of layered system. In fact, the RPS are being done more in the 4HB case, but indeed this is one of the type of measurements where one again could distinguish this type of a scenario. And I think I'm coming now to the end of my talk. And basically what I wanted to show with these results, first of all, is the power of DMFT calculations, which is able to give us information about the nature of these features observed in STM. Moreover, that these type of systems offer a new platform for investigating, in fact, heavily doped Mott insulators. If we think about the high TC cuprates, where we have a lot of dope Mott physics, but the dopings are small. Here we are talking about getting dopings, in fact, by manipulating on the distance. And I didn't talk about that, but one can manipulate the distance between the two layers, but one can also manipulate let's say the sheaves. So in fact, Moiré type of displacement between the two. And these gives the possibility to investigate the physics of these very dope Mott systems and on a triangular lattice. So basically my my end words is by saying that these systems, in fact, are extremely interesting, not only because of all the moire physics that we already saw in the first talk, but because one can play also with all these doping effects and further. And because I'm at the end, I thank you very much for your attention. I'm happy to answer questions.
Thank you very much.
Thank you very much, Rosaire. Do we have any questions in the chat? Paul, go ahead.
Thanks for the nice talk. I'm wondering, since this 1T tantal disulfide was, for example, considered by the group of Fausti to induce some phase transitions using the electromagnetic environment. How far do you have an estimate of how far you would have to separate these two layers in order for the charge transfer effects that you focused on to no longer appear? To use this as a platform to screen with plasmons.
So basically, yeah. So let me I think that the most significant one is this one here. So basically what you want is the question is whether if you want to have a critical distance where you can treat the 1T layer as basically independent of the 1H, right?
Mm-hmm.
So this distance, in fact, I don't have the figure here further, but the distance is about, I think it was 9 Armstrong, where you really have that the two are not anymore. So basically you have a completely half filled 1T. It's about 9 Armstrong, as far as I remember, because here I didn't show the figure, but this is the distance where you basically are not anymore going to have charge transfer effects.
Thank you very much.
Andy?
Hi. Yeah, thank you. Just, I realize I missed one other point. When you consider the case of substantial charge transfer between the layers, does the, as it were, Star of David lattice distortion change? Or is that kept fixed?
Question. Well, so indeed, what we did, this calculation at the DFT level, the relaxation was done really by allowing also what happens to the charge to the Star of David, and the changes are very small. So in fact, it remains very robust. These Star of David, they remain very robust, even if you have some doping, some charge transfer.
Interesting.
At the level of the DFT, it's pretty robust.
Thanks.
Can I ask just a naive question?
Yeah, Henry.
Sure.
Experimentally, how does one control the distance between the layers?
Well, I was talking to Peter Lilienroth about that, about how much they can control this distance, and he was telling me that at least the way they are growing, these two layers, so basically they have a substrate of graphite, and then these layers, they crawl one on top of the other. So they have regions where they see only one layer, regions where they see the two, and this crawling, the distance is something that comes in the growth. At that moment, they were not they were not being able to really control it very much, but now they are building devices. He was telling me, and it seems that with a device, they will be able to have a much better control of these distances. But you are the experimentalist. I don't know more than what I was told by Peter.
But I'm actually surprised the distance can be controlled at all. I mean, I would have thought it's just
This
controlled by the basic
that's
energetics.
that's what they were saying, that it basically grows the way it grows, but they are now building devices where it seems that they will be able to control it better, but I'm not sure whether they are successful or they will be successful on that.
Change the screening, maybe.
Yeah.
Some substrate.
and unless
By using, exactly, by using
to tilt, and
plates.
they are able to tilt, and in that case they would have a progressive change of the distance, and so they could isolate the regions. I don't know. It seems to me a rather strange way.
Yeah, it's probably difficult, at least if one looks at the pictures that they show, where you basically have everything on a large scale. On a larger scale, if you look at, you have regions of bilayers, regions of monolayers, and
I understand the point.
yeah.
That's the interest of disorder, which allows you to pick up ordered parts and well, I can understand that.
Yeah.
But it will always be a little bit difficult point to compare to a theory which likes well-defined spacing.
Yeah, well, I don't know whether working with the bulk gives you more options, but so let's say that you take the bulk and then you intercalate between. So if you look at the bulk, I had the picture of the bulk, whether by intercalating, and I think this is also another option, that you take the bulk where you already have that built in, and then you start intercalating things in between. This is another option to change the distance between these layers.